And in effect, if you have a, what does this describe? If you have let's say a hula loop filled with some kind of a liquid, and you have a non-equilibrium temperature distribution within the liquid, and you somehow drive the liquid to go like into one direction, right? Then this is the equation that describes the temperature distribution. If you have no kappa, that means the liquid has no conductivity. That means the temperature just follows the movement of the liquid without ever decrease in the maximum or increase in the minimum. But if you have a non-zero conductivity, right, the temperature is going to actually move around in a shape and gets smoother and smoother, eventually uniform over time. So this is the kind of equation described. Okay, so to start solving this equation, we need to figure out how to approximate the second order derivative. Now you have seen a lot of approximations of derivatives now. What approach would you start by finding a good approximation for the second order derivative? Yes?
Could you turn the term on the right into its own matrix like A?
Yeah? Sure.
For the eigenvalues.
Well, if I already have a method of discretization, then I can follow the discretization and turn it into a matrix and look at its eigenvalues for stability analysis, right? But how do I get the approximations to start? Do you remember in ODEs, we did a little bit of analysis in trying to construct schemes ourselves, right? How do we get a scheme to approximate time derivative in this case with really to be as accurate as possible? Do you remember how we did that? Well, let me basically give you kind of a tour again of how to do that. But now this time we're going to be focusing on the second derivative. So the idea is, how do I approximate the second order derivative at a grid point I by some linear combination of the neighboring grid points? All right. So let's first of all try what we have done before, right? C1 times ui minus 1 plus C2 times ui. Okay, so let's try these 2 points and to see if we can get a bunch of coefficients to approximate the second order derivative. How do we start? We're going to be writing Taylor series, right? Ui minus 1 is going to be equal to, let me write the equal sign a little bit further, so then I'm later going to add C1. Ui minus 1 is equal to ui, okay, minus the first order derivative. Now let me just write the derivative out, because we have 2 derivatives at I, times what? Delta x, right? Taylor series. Somebody tell me the term afterwards. What is it? If I expand the ui minus 1 in terms of Taylor series. Yeah, delta x squared over 2, right? Actually 2 factorial, which is equal to 2 times second derivative, right? Again at I. Okay, so let's just say let's just expand one more term. So delta x cubed over now 3 factorial, right? Which is 6, and third order derivative of x And let's just start our own notation, delta x to the fourth. Okay, how about ui? Ui is equal to, well, ui plus 0, 0, 0, 0, right? Oh yeah, thank you. The cube term should be negative delta x. Thank you. Okay, so now multiplied by the coefficients. C1 times this is equal to C1 times this, C1 times this, C1, C1, and O delta x fourth doesn't change. And C2 times this is plus C2 plus 0, right? Okay. Now, our goal is to get what? Get a good approximation to which part of this expansion? This, right? This is what we want. We want to approximate this guy. In order to approximate this guy, we can see immediately that we have to divide this whole thing by delta x squared, right? Okay, by something proportional to delta x squared. Okay, which means I have to also divide this, this and this by, this and this by delta x squared. If we do that, and if we want to get a good approximation that shrink to 0 as delta x goes to 0, we would need to make both of these terms to be 0, right? We have to cancel out this and this. Now we look at the second term. Because this is 0, in order to cancel this out, C1 has to be 0, right? So we have 0. And in order for this to cancel out, now my C1 is 0, C2 also has to be 0. So I have 0. I have a scheme that is 0. And of course, then I actually cannot get my second order derivative because this is 0. So what can I do? What's wrong with this approach?